module. You will learn about the dynamics of rotational motion of a rigid body about a fixed axis. Using the analogy of translational motion and rotational motion, we know that the moment of inertia is the rotational analog of mass in translational motion. Similarly, torque in rotational motion plays the same role as that of force in linear motion. We will now try to derive the expressions for a rotational body about a fixed axis, keeping in mind the dynamics of the system. For simplification purposes, we will consider the rigid body to be rotating about a fixed axis. As the axis is fixed, only the components of torque, which are along the axis of rotation, can cause the body to rotate about the axis. For example, if a body is rotating about a fixed z-axis, then only tau z, a component of torque along the axis of rotation, can cause such rotation. We know that torque tau is equal to R cross F. Thus, the torque acting along the axis of rotation must be perpendicular to the plane containing the position vectors and force. Thus, to calculate torque acting on such a rigid body, we will consider only those forces which lie in a plane perpendicular to the axis of rotation, so that the torque produced by them will lie along the axis of rotation. Only the components of position vectors that lie in a plane perpendicular to the axis of rotation need to be considered for the torque along the axis of rotation. Let's now try to find the work done by the torque for a rigid body rotating about a fixed axis, keeping these considerations in mind. Consider a particle in a rigid body located at P, with its position vector represented by R. The rigid body is rotating about the z-axis. Now, construct a plane containing the particle at P and perpendicular to the axis of rotation. Let us call it the x-y' plane. When the rigid body is in rotational motion, the point P moves along a circle with its center at A. Let the radius of the circle be R1. We can see that the position vector OP is equal to the sum of OA and AP. Thus, OP is equal to OA plus AP. In fact, we see that AP is the component of OP in the x-y' plane. F1 is a force in the x-y' plane acting on the particle at P and makes an angle alpha 1 with the radius vector AP. When the rigid body is in rotational motion, the particle P moves in a circular path, and its position changes from P to P' in a small time interval delta t as shown. The angular displacement of the particle is expressed as angle PA' and is equal to d theta. If the linear displacement of the particle is represented by ds, then its magnitude ds is equal to r1 d theta. Let this be equation 1. A tangent drawn to the circle at P represents the direction of ds. Phi 1 is the angle between the tangent at P and the force F1. From the figure, we see that phi 1 plus alpha 1 is equal to 90 degrees. Let's now find the work done. The work done by the force F1 is dW1 is equal to F1 dot ds, which is equal to F1 into ds cos phi 1. Since phi 1 plus alpha 1 is equal to 90 degrees, thus phi 1 is equal to 90 degrees minus alpha 1. Substituting the value of phi 1 from above, we get dW1 is equal to F1 into ds cos 90 degrees minus alpha 1 equal to F1 into ds sin alpha 1. Substituting the value of ds from equation 1, ds is equal to r1 d theta, we get dW1 is equal to F1 into r1 d theta into sin alpha 1, which is equal to F1 r1 sin alpha 1 into d theta. Since F1 r1 sin alpha 1 is equal to r1 cross F1, we have dW1 is equal to r1 cross F1 into d theta. Substituting tau 1 is equal to r1 cross F1. Thus, dW1 is equal to tau 1 d theta. Let this be equation 2. Here, tau 1 is equal to r1 cross F1 is the torque on the particle along the axis of rotation due to the force F1. If there is more than one force acting on the body, and the work done by different forces is represented by dW2, dW3, and so on, then the work done by all the forces acting on the body, dW, is equal to dW1 plus dW2 plus and so on, which is equal to tau 1 d theta plus tau 2 d theta and so on, equal to tau 1 plus tau 2 and so on into d theta. Since all these torques are along the axis of rotation, we get the total torque on the body as tau is equal to tau 1 plus tau 2 and so on. Therefore, the work done by the total torque acting on a body rotating about a fixed axis is dW is equal to tau d theta. Let this be equation 3. Comparing equation 3 with its translational analogy, where the work done by a force is denoted by dW is equal to Fds, we can see that torque is the rotational analogy of force. Now, let's try to find the rate of doing work, also known as power. We can differentiate equation 3 for the work done by the total torque acting on a body rotating about a fixed axis to find instantaneous power. On differentiating equation 3, dW is equal to tau d theta. We get dW by dt is equal to tau into d theta by dt. But since angular velocity omega is equal to d theta by dt, we get dw by dt is equal to tau omega. However, we know that dw by dt, the rate of work done, is known as power. Thus, power P is equal to dw by dt. We get P is equal to tau omega. Let this be equation 4. Equation 4 is the value of P, which is the instantaneous power. When work is done on a rotating body, its energy must increase. However, in the case of a rigid body, the change in its potential energy must be zero, as there is no change in intermolecular distances. Hence, the increase in energy when work is done on a rotating rigid body increases the kinetic energy of the body. Therefore, the rate of work done on a rigid body rotating about a fixed axis must be equal to the rate of increase in its rotational kinetic energy. We know that the rotational kinetic energy of a rigid body is expressed as Kr is equal to half I omega square. Let this be equation 5. On differentiating equation 5 above, we get the rate of work done, or power, equal to the rate of change of kinetic energy. Thus, we get P is equal to dKr by dt. Substituting the value of P from equation 4, P is equal to tau omega, and Kr from equation 5. Kr is equal to half I omega square. We get tau omega is equal to d half I omega square by dt. Equal to I by 2 into 2 omega d omega by dt, which is equal to I omega alpha, where angular acceleration alpha is equal to d omega by dt. Therefore, tau is equal to I alpha. Let this be equation 6. Equation 6, tau is equal to I alpha, is Newton's second law of rotational motion. It states that the angular acceleration of a rotating body is directly proportional to the applied torque and is inversely proportional to the moment of inertia of the body. You have now reached the end of this module. In this module, you learnt that the work done by the total torque acting on a body rotating about a fixed axis is dw is equal to tau d theta. We know that the rate of doing work is known as power. Instantaneous power, P, is equal to dw by dt, which is equal to tau omega. When work is done on a rotating body, its energy must increase. Therefore, the rate of work done on the rigid body rotating about a fixed axis must be equal to the rate of increase in its rotational kinetic energy. We know that the rotational kinetic energy of a rigid body is denoted by Kr is equal to half I omega square. The equation tau is equal to I alpha is the Newton's second law for rotational motion. It states that the angular acceleration of a rotating body is directly proportional to the applied torque and is inversely proportional to the moment of inertia of the body.